So we turn now to some limit laws. Um, these rules have to do with how we combine limits that we already know. So let me just highlight these over here. So if we know the following, if we know that the limit of one function as x approaches c is L, and the limit of another function as x approaches the same point c is a different limit that we'll call m. What these rules tell us is how we can combine them. So the first rule, let me just write an example column here, and I'll just give you a couple of examples of each of these. So for example, this is what's called the sum rule. And what it says is that if you have the limit of the sum of two functions, you can simply add the limits. So just for example, the limit as x approaches 1 of x squared plus 5. Actually, let me just make it a little easier. Yeah, 5 is good. That's good. So this is equal to the limit as x approaches 1 of x squared plus the limit as x approaches 1 of 5, which itself, each of those limits, recall that these limits can be evaluated by the substitution rule that we just did. So this is going to be 1 squared plus, if you substitute 1 in for x every place it appears in the function 5, x doesn't appear, so that's just 5. So this is going to be equal to 6. This is the difference rule. Sorry, you can't really see that. Difference rule. And it works the same way. It just says if you take the limit of one function minus the other, you can simply subtract the two limits. You can see an example of that in the textbook. I don't think I need to do one. Next one, let's go to, this is constant multiple, it's often called. And what this says is if you assume that k is not a function but rather some constant, this is rule number 3, we can, if you know the limit of the function, then the limit of k times that function is just k times the limit. So for example, the limit as x approaches 2 of 3x cubed is equal to 3 times the limit as x approaches 2 of x cubed. So that's going to be 3 times 2 cubed, which is 2 cubed is 8, so that's 3 times 8, which is 24. Okay, next rule is the product rule. That works, again, fairly similarly. What it says, for example, is that if the limit as x approaches, let's say, 2 of x squared e to the x, that's going to equal the limit as x approaches 2 of x squared times the limit as x approaches 2 of e to the x. Now recall again that these are both limits that can be evaluated by substitution, so this is just going to equal 2 squared times e to the 2, so that's going to be 4e squared. And in general, these these all work similarly to each other. Put up the numbers that these relate to. 2, we won't do an example. 3, 4. So 5, we have we have a limit of a quotient. The only thing that's different about the rule for the limit of a quotient, limit of f of x over g of x, is that you can apply the same rule. It's just the limit of the quotient is just going to be the quotient of the limits as long as the limit of the bottom function is not 0, because you can't divide by 0. So the idea is that if I find the limit as x approaches, let's say 2 of x squared plus 1 over x minus 1, that's just going to be, I'm going to substitute in, that's going to be 5 squared plus 1 over 2 minus 1, so that's going to be 26 over 1, or 26. But if instead I take the limit as x approaches 1 of x squared plus 1 over x minus 1, that gives 0 in the denominator, so the rule doesn't apply. In this case, we need a different rule, which we'll cover a little bit later. So let's see, 6. 6 and 7 are really the same rule, because you know, of course, that a radical, if I take the nth root of something, that's like raising it to the 1 over n power. So, but just to be clear what we're talking about, if I know, for example, that suppose that I know that the limit as x approaches 2 of f of x is equal to 10, then I know that that implies that the limit as x approaches 2 of f of x cubed is equal to 10 cubed or 1000. And 7, I can do the same thing with roots. So the limit as x approaches 2 of, I should just going to highlight this. In other words, this is something we're given. I'm not saying that it's always the case that the limit of f of x is equal to 10. I'm saying I'm giving it some function where the limit of f of x is 10. Let's use that same function here. If I do this and say what's the limit of the square root of f of x, and I'll keep that color, then this is just going to equal the square root of 10 because I can just because I can just take the square root of the limit that way. So we want to see how these limit rules work in practice. So let me just show you the rule as applied. Normally, you're not going to do limits quite as in quite a detailed oriented way as I'm about to do them, but I just want to show you how the limits work, how the limit rules work, and eventually you develop sort of an intuition about how much of this you need to write. So what we know is that by the sum and difference rules, this limit that's given here is going to equal the limit as x approaches 2 of x cubed plus the limit as x approaches 2 of 4x squared plus, sorry, minus the limit as x approaches 2 of 3. So this is just an application of the sum and difference rules. Now we can break this up even a little bit more. We can say that this is equal to the limit as x approaches 2 of x cubed. I could use the power rule actually and turn it into the limit of x all raised to the third power, but it's just not necessary because this is a polynomial. So this is going to equal, now using the constant multiple rule, this is going to equal 4 times the limit as x approaches 2 of x squared, and then minus the limit as x approaches 2 of 3. So this is constant multiple. Keep in mind that this was a polynomial function, so I could have just substituted in to begin with, but this is just in the very basic demonstration of how these limit rules apply, because there are going to be some functions where you can't just say this is a polynomial, the substitution applies. So let's go to the next step. So we can now substitute. So this is going to be 2 cubed plus 4 times 2 squared minus 3. And so that's going to equal 8 plus 4 times 4 is 16 minus 3. And I believe if I can do my arithmetic correct, that comes out correctly, that comes out to 21. Let's do another one, just involving a couple of different rules. So this one is going to be this looks like on the outside it's going to be a quotient. So we start out this way, and this is where the notation starts to get a little bit confusing. We take the limit as x approaches 1 of x plus 7 over the limit as x approaches 1 of the square root of 2x squared plus 3. So that's going to be an example of, that's going to be an example of the quotient rule. And we can verify, by the way, that substituting in 1 does not give us 0, so we don't have a division by 0 problem and we can proceed. We know that the quotient rule applies because at x equals 1, the denominator is not equal to 0, so you don't have a division by 0 problem. Okay, next we're going to break this up further. This becomes the limit as x approaches 1 of x plus the limit as x approaches 1 of 7 over the square root of the limit as x approaches 1 of 2x squared plus 3. So this now becomes an application of the sum rule on top and the root rule, that was rule number 7 from the other page, on the bottom. And we can do even one more of these. We can say is equals the limit as x approaches 1 of x plus limit as x approaches 1 of 7 over the square root of the limit as x approaches, actually we'll do 2 more of these because we've got actually a constant multiple times the limit as x approaches 1 of x squared plus the limit as x approaches 1 of 3. So that's going to equal 1 plus 7 over the square root of 2 times 1 plus 3. So that equals 8 over, I believe this comes out to root 5. There we go. Oh, and by the way, I know that I get this question every year. You say, don't I have to take this root five and multiply by root five over root five to get rid of the radical in the denominator? Not really. This is not algebra class. It's calculus class. We'll accept a root in the denominator. Sometimes that's even the better way to write the number. So here's a little bit more abstract example of what you can do with the limit laws. Um, so let's suppose the limit as x approaches 1 of f of x minus 5 over x minus 2 is equal to 8. What we want to do is we want to find what the limit as x approaches 1 of f of x is. Now keep in mind, it looks almost like we're just trying to find f of 1, but we're not. Because remember, the earlier example showed that it may be the case that, that f of 1, it may be the case that f of x looks something like this, where the limit as x approaches 1 is actually going to be different from the value at f of 1. So you can't just totally gloss over the issue and say, surely I'm just solving for f of 1. That's not what we're doing. So what we'll do is we want to set up this equation this way. So let's write the limit. We have the equation here. I'm going to break it down. I'm going to say the limit as x approaches 1 of f of x minus the limit as x approaches 1 of 5 over the limit as x approaches 1 of x minus 2, or sorry, yes, is equal to 8. Okay, well, there are certain limits here that we can evaluate, because we can evaluate this limit here. That's a polynomial or a constant, so we can do that by substitution. And we have this limit here, which is also a limit of a polynomial, so we can evaluate it by substitution. So let's do that and just rewrite this equation. This is going to be the limit as x approaches 1 of f of x. That's the one we can't do by substitution. Minus 5 over, by substitution, that's going to be 1 minus 2, which is negative 1, is equal to, on that side, 8. Let me bring the equation up here. So this gives us the limit as x approaches 1 of f of x minus 5 is equal to negative 8. I'm just multiplying both sides of the equation by negative 1. Now I'm just going to add 5 to both sides, and that gives us the limit as x approaches 1 of f of x equals negative 8 plus 5 is negative 3. So that's the answer to that question.